Today we are finally going to do some work in Physics 20. Work which we define as the change in energy experienced by an object. So let's say a car is sitting at a stop sign, and then the car is not sitting at a stop sign because the driver puts the foot on the accelerator and speeds the car up. There must have been work done on the car in order to get it to speed up because that car experienced a change in energy. If we are to calculate the amount of change in energy that car experiences, then we will find the work that was done on the car. There are two things that are required for work to be done on an object. Does anybody want to take a stab at what one or both of them are? What do you have to do to change the energy of an object, to do work on an object, Holly? Okay, there has to be movement. Yes, there has to be movement. If you don't have movement or a displacement, then you can't change its energy. Think about it. Your desk right now, and you for that matter, sitting at your desk right now has 0 joules of energy. If it doesn't move, then its energy isn't going to change. You can't give it energy, or for that matter, take energy away, because work can be either way, right? Add or subtract energy without moving that desk. What else? How are you going to move that desk? Push it or pull it. So you got to apply a force. In order for work to be done, in order for there to be a change in energy, you have to apply a force. And that force has to cause movement. It's not enough to just push the desk, right? I'm pushing Danny's desk right now. It isn't moving. The energy of that desk hasn't changed, right? So no work has been done on it. Force is important, but it's not enough. You have to have force and movement to actually have a change, a gain or a loss of energy. So it depends upon two things: the force acting on the object and the displacement of the object, the movement of the object. Now listen to this. We said that we have to have a force and a displacement, but we have to have a force and a displacement in the same direction. In other words, if a wagon is rolling down the street horizontally, and I jump on the wagon and apply a force downwards on that wagon, I'm not doing any work on the wagon because my force isn't contributing to the motion of that wagon, right? I'm not causing the wagon to speed up. I'm not increasing or decreasing the energy of the wagon by jumping onto the wagon. So applying a force vertically with motion horizontal doesn't do anything. If I want to do work on this wagon, I have to apply a force horizontally on the wagon that's moving horizontally. Now, sometimes you guys know that as I pull a wagon, in fact, most times I pull a wagon, I pull it at an angle. Well, does that count? If the wagon is moving this way, but I pull on it this way, yeah, that counts, or at least part of it counts. The x component of that force would count because the x component of that force is parallel to the way the wagon is moving. But the y component would not count. So this counts, this doesn't, this doesn't. What you have to do there is find, in that case, the x component of the force. The good news is that the work equation kind of does that for us. Work is equal to force times displacement, but we often see a cos theta tacked onto the end of it. What's the significance of the cos theta? Look back at the picture I drew a second ago. If this is theta, then saying cos theta finds for us the x component of that force. So in other words, when you give in the equation W is equal to FD cos theta, it allows you to find the x component without doing anything else. The equation does it for you. What if the object moves this way and I apply a force this way? What's the angle? The angle between the way that it moves and the way that I apply the force. What's the angle there? 0. What's cos 0? 1. So the equation becomes F times D, right? If I pull it this way and it moves this way, what's theta? 30. So my work would be F times D times cosine theta. In other words, the x component of the force times the displacement. Oh, what about this one? This one's a great one. What's theta there? No, theta's not 30 there. That's a trick question, though. I set you up to get that one wrong. What's theta there? Kelly? No, not 90. 0. Good. Why is it 0, Nick? Yeah, if it's moving, if this box is moving like this way, which way is it being pulled? This way, right? Theta represents the angle between the way that it is pushed or pulled. In other words, the angle between the force and the displacement. Sometimes even in a case like this, we have an angle, but we don't use it because that angle isn't significant. We're going to say F is the force. And of course, force is in newtons and it's a vector. Delta D is the displacement in meters, and it's a vector as well. And theta, this is the tricky one. Theta is the angle, but not just any angle. It's the angle between the force and displacement. I'll be honest with you. Most times you get a question on work, the angle is going to be 0. And if the angle is 0, because it's pulled in the same direction as it moves, which again is most of the questions, then if you want, you can just drop the cos theta. You can put it on if you want and include cosine 0. But if 0 is theta, then you don't even have to bother putting in cos theta because you know that the equation is going to ultimately boil down to F times D. So a lot of times we're going to use F times D. If there is an angle, though, and the angle is not 0, then we're going to include F times D times cosine theta. Let's have a look at another example, 294. This one says we have a force of 150 newtons, and we have a movement, a displacement of 25 meters at 25 degrees. What's the work done by this force? Well, usually we say work is equal to force times displacement. And it is, but we have to recognize that force and displacement have to be in the same direction. Are these in the same direction? No, there isn't. So really what we got to do is find a component of the force that acts in the direction of the displacement. What's the easiest way to do that? Just tack on cos theta on the end of that equation. On your data sheet, it actually says work is equal to FD cosine theta. So just use the form of it that appears on your data sheet if you've got an angle. F is 150 newtons. Delta D is 25 meters. Good question. That's a really good question. We'll talk about that in just a second here. What's theta? Remember, we don't automatically, if we're given an angle, put it into the FD cos theta. Do we include it here? Yep. Because that angle has to represent the angle between the way that it moves and the way that it's pushed. And clearly that's the angle that we're given here. So we're going to include that, 25.0 degrees. Let's figure out the value of work here now. What is it? Okay, and we're going to round that to 3 significant digits, 3.40 times 10 to the 3. And what would the units for work be? What did we define work as? No, that was energy, the ability to do work. Work is defined as the change in energy. The change in energy. The change in energy should be measured in what units? Joules. Okay, this is going to be 3.40 times 10 to the 3 joules. Would work be a vector or a scalar? It'd be a scalar, right? If energy is a scalar, then the change in energy has to be a scalar as well. This is kind of weird though. Hey, look, vector times a vector gives me a scalar. It's kind of like a negative times a negative gives me a positive, right? Positive times a positive gives me a pos. A neg times a neg gives me a positive. Just like a scalar times a scalar gives me a scalar, and a vector times a vector gives me a scalar. So it's kind of like vector is a negative, and scalar is a positive in a sense. All right, let's have a look at these questions on page 294. All four of them. Holy cow. Give you a few minutes to work on those now.